If you don't want to come to lab physically in person, go through into the lab folder in BB Learn, do this tonight, and see if you can at least open the Pixis Project Navigator. There's directions in BB Learn.
I have a question, Julie. So
yes.
despite the lab saying it's due tomorrow, it's actually really due next week?
I fixed it.
All right.
Okay.
Thanks.
Right. Enough people told me that nobody emailed me, so nobody got extra credit points for that. Okay, so content, I just thought of it myself. I nearly sent EE380 an email and told them they were full of it. Content, lab materials, there's a pre-lab that's due. Before that, you need to get that done. That requires hunting through the book. This is a link to something that was written to get you into the system. People have done this successfully. Your lab team number is in this file. Make sure you set up this remote connection before lab, because it can take you up to like half the lab to do that. And you may need the time to actually do the lab. It's a little, Mentor is a little fussy the first time you use it. There is unique data for your team number. It's in this file. This is the lab 1. It's just basically lab 1 and lab 2. You basically just fill in the blanks and turn it in. For lab 3 and lab 4, you have to write a formal lab report. Your pre-lab is due Friday, January 22nd. That's the pre-lab, not the lab. The actual lab is due Friday, January 29th. So there is something due this Friday, and it's just the pre-lab assignment. That's about it. Okay. We'll go through all of lab 1, and then next week we're just having a quiz on lab 1. And let me point this out to you. People don't believe me until like lab 3 or lab 4. Here is your lab. Let me point out a few features of this. They've been Browerized. Okay, you've got some numbers up here you can use for anything in your thing. That is right, I've updated it. The pre-lab is worth 10 points. Filling in the blanks in here is worth 20 points. The evidence section is worth 40 points. If you don't do the evidence section, you get a 20 out of 60 on your lab, okay? So please do that. The quiz is worth 30 points. We will do the quiz in lab next week. That will be the entire lab is just sitting there and doing the quiz. The quiz is, if you look at these instructor questions, you're going to get one of these 3 instructor questions as your quiz. And people don't believe me. If you want to know what to study, look at the instructor questions. This is the evidence part. There's 2 voltage transfer curves over here. You look at them and you kind of eyeball them and you estimate all the values for VOH and VOL and VMIN and for all the stuff you're measuring in lab based on these curves. And you get a surprisingly similar thing on the quiz. So this evidence part is just making sure you understood what you measured, and it is 40 out of 60 points of the lab. So please do that part. And we've got graders that I think will actually grade in a more timely manner this semester. And we've got extra tests. What more could you ask for? I may be able to do midterm grades in the class. Let's see what else. Homework 2 is due a week from today. Be generous with your timing. Most of the assignments in here are a little long, a little confusing, but they will, if you understand the assignments, the labs, the stuff you're doing in lab, the stuff you're doing on the homework, compared to them, the exams are a piece of cake. That said, the exams are hard. Where are we at? We want to talk about CMOS inverter delay and power. I think we had some of this, most of this was in 280 still. When we go to the next set of slides, starting on Thursday, we will get into more, or starting on Tuesday, next class, we will get into some of the more advanced CMOS concepts, and this will be new material for this course. And then it just keeps getting deeper. Okay. We want to think about dynamic power, what's happening as a function of time. Generally, we want the power consumption on our CMOS devices to be as low as possible. Power translates into my battery. High power means my battery does not last as long. That's one reason why I want it low. Another reason is that power is going to be dissipated as heat on the chip. And heat on the chip is a big thing. It degrades the performance. It could possibly burn your chip out. Intel's latest processor, it has this thing on it, and most chips now do too, have this thing on it called dark silicon. It's basically, I can only run 75% of this chip at one time and not have it blow up because the heat gets to be too high. It actually damages the device. Heat's a big issue. That I talk about it a lot. But we want to keep the heat down. Now, as far as the delays go, we want the data going through our processor as fast as possible, because then I can get more data out to the consumer. My Zoom screen doesn't freeze, which it probably will today. All those good things. If I can get faster, I'm going to have better performance. But the big caveat here is that when if I want faster delays, I have to use more power. So there's a trade-off between speed and power. I have to find out what's right for my particular design. There's never one right answer. Now, the individual delays for each circuit I've got in here, I've got a register, and this register is going to clock the data out on a rising clock edge. We'll just call everything rising edge. And when it clocks it out on the rising clock edge, it's going to take some small amount of time to actually get to the circuits in the combinational logic block. Once it gets to the circuits in here, those circuits have to settle into their new state. So this is the delay of the combinational logic. And they have to settle long enough before the next clock edge to ensure that this register has the correct data in it. So that's the setup time. Okay. And plus I want to put some margin in there because some of these circuits may be a little bit smaller, some of them may be a little bit slower. So typically we designed with a 50% margin. We designed so that we had everything settling in a half a clock cycle to give us a half a clock cycle for unexpected delays. We want it to settle, the whole thing to settle in a clock cycle so that the next operation can happen. So keeping these delays as short as possible means I can speed up my clock and get more data out. Everybody wants more data.
Sorry, what was that clock minus Q time? What does that mean?
The clock Q, it's the amount of time that it takes after the clock edge before the data is valid on the output of the register.
Yes.
Okay. So when we measure these delays, we've got some conventions here. I've got this is the output high level, this is the output low level. The convention is that I measure between 90% and 10% on these rising edges and falling edges. Reason why 10% is it means that it's definitely started changing, and 90% means it's almost there. I don't have to get up to 100% because this is a digital level. This is the input signal. And for the input signal, we call the rise and fall time, the conventional name for rise and fall time, we call that T rise and T fall. So that would be, the rise time would be this interval between 10 and 90 on A. And the fall time would be going from 90 to 10 on the falling edge. And that's what is B here. Now I can do the same thing on the output of the inverter. I can't call it the same thing. If I call it T rise and T fall, it just confuses people. So they had to give it a new name. So going from 90% to 10% is the fall time on the output. And that's E. We call that T transition, and the output's going from high to low. So that's TTHL. T transition high to low. And on the other side of that, I've got the rise time, which is T transition low to high. These are the things you'll be measuring in lab this week. Now, there's another thing that's important too for this inverter. How long does it take for changes on the input to actually make it to the output? And we call those propagation delays. So that's where the P comes from. And what I want to do here is I want to make sure the inputs actually started changing. So here I'm using the 50% level. So going from 50% on the input, where is that? To 50% on the input, it drops down to here, to 50% on the output, that's this time interval C. The output's going from high to low. So this is T propagation high to low, C. The high to low is what's going on the output and not what's going on in the input. On the other side here, I have 50% on the input to 50% on the output. The output's going D. Oh no, not this again. Give me a minute. There we go. Okay. We call that T propagation low to high. I have to stop talking for my technology issues. Okay. How do I tell when I'm just looking at these two signals on the screen, which one is the input and which one's the output? The output's reacting to a change in the input. So it's going to always happen later. And you can see the input's changing first, and then the output starts to react. So if I see these two on a single graph, I can tell which one is the input and which one's the output by which one happens first. Okay.
The time propagation low to high, that should be D, right?
D, yes, you're right. T propagation low to high. Yeah, that's a D. I got two F's on there, you're right. Thank you. Thank you, Amelia. We've got this one right here. This is actual real looking data. And I've put this on a test, and I'm just amazed at the people who get this wrong. The percentage of class answer. The first thing I ask you is, okay, you've got a signal that looks like this. Which one's the input and which one's the output? Input's got to happen first. So this signal right here is the input, and the output is taking a little bit longer to react. This must be the output. I've got 25 picoseconds per division. So 100 picoseconds would be 4 little blocks away, would be right about there. And then we've got, did I do this? Yeah, I did. Good, because I'm not going to draw this. And here I've got 1, 2, 3, 4, 5, 6 blocks going from 0 to 1.8. So each one of these must be 0.3. If I want to measure my 10% level, it's 10% of 1.8 is going to be 0.18 volts. So that would be right about here. And my 90% would be 1.58, would be right about up here. And my 50% would be 0.9, and that would be right there in the middle. Okay, so there's a much neater graph than I can draw with this stupid pen right here that shows you the 90%, I calculated that wrong in my head, the 90%, the 10% level, the 50% level, and it's actually measuring those delays. This is what we get to do in lab tomorrow. Okay, we'll go through it. All right. Okay, capacitance. All these capacitors are real. A single MOSFET. They're models of delays within the MOSFET. The physical, like if you think like the gate to source capacitance here, it's part of the gate itself. But there's other things in the physics of this that are causing delays. We force this into a linear model to get a better approximation of what's going on. And with the timing, we need to add all these capacitors in. Now, the convention for naming these things, if I look at a capacitor here, this is the gate, and this is the drain. Capacitor B is going between the gate to drain. I would call that CGD. It's got 2 subscripts, and the subscripts tell you which terminals it connects between. Now, the convention that people have developed is that G always comes first, and the body always comes last, and everything else will just fall into place. So this is going between the gate to drain at CG to D. This is the source, so C must be CGS. E is going between the gate, and this is the body over here. The body always comes last. This is C, gate to body. A is going between the drain and the body always goes last. C, drain to body. And D is going between the source and the body, so this is CSB. All capacitors, and thank goodness, Metagraphics handles this for you. In your SPICE model file, well, I call it a SPICE deck. It used to literally be a deck of cards back in the day. But it has a listing of all these capacitors in there and what the expected values are for your transistor. In different regions of operation, these capacitors have different values. Some of the capacitors are voltage dependent. The capacitance depends upon the voltages applied. So you literally have to go through and figure out what's my bias point for this transistor, calculate the capacitors, and then figure out the effects of the delay. This is why we're glad we have simulators to do this for us. It's more complicated than that you can do. When you estimate the delays for your pre-lab, if you get a number that's within a factor of 10, I will be overjoyed. The estimates are based upon what is the dominant effect, but there's a lot of other effects in there. If you really want an accurate answer, you have to go to simulation. And even that might be off slightly from what you build on any given day, because the parameters change from day to day depending on lots of things. When I'm calculating a delay for an inverter, all those capacitors are actually in the circuit, and they have to be taken into account. It would be a mess to have to do that by hand. But if you want to think about what you can what you can grasp that you can actually use, remember this is an inverter. When if I have a signal that's starting out at 0 on the input, that means this one output is starting out as high. So when I switch the input to VDD, suddenly this goes to VDD. What's going to happen here is point is going to have to go low. So these capacitors that are initially charged are going to have to discharge. And that charging and discharging is what's going to take time. This is where the delays are coming from. To discharge the capacitors, I'm always going to discharge through this one, through the NMOS, because it's got the tie to ground. When I'm charging the capacitors, I'm going to have to charge through the PMOS, because it has the tie to VDD. PMOS is slow by about a factor of 2.5. So what we typically do is we make the PMOS transistors 2.5 times bigger to compensate for that and to balance out the charging and discharging time. Oh, I love going to lab. It makes me realize what you guys know and don't know. Okay, well, I want to talk about.
I have a question.
Yay.
So are the PMOS and the NMOS, are they essentially acting like a pull down and pull up resistor?
Yes.
All right.
And sometimes you take, and it's like you effectively can like pull the pull down resistor out of the network, and sometimes you can pull the pull up resistor out of the network. It went through the magic of switching transistors on and off. Okay. When I'm not going to lab, I forget about things like this. Okay, fan out. This inverter right here, if I draw this back in my 110 version of this, I have one inverter driving another inverter. That's all we're seeing down here. I've added the transistors in, I've added the capacitors in that Mentor's going to take care of for me. This is called a fan out of 1. Now, if I had a fan out of 2, the things you missed by not using TTL gates, it looks like this. I have one inverter driving 2 inverters. Now we can go back to this capacitance model here. If I stick another inverter in here, I've got twice as much capacitance. So this is driving like C, this is driving like 2C. Which one do you think is going to switch faster, a fan out of 1 or a fan out of 2? No takers. This is going to be much slower. So typically when we were designing our standard cells, what we would do is we would design them to have acceptable delays up to a fan out of 10. And we always limited our fan outs to 10. What you're going to be asked to do in the lab is to measure the delay with a fan out of 0 equals 0, which just means that it is driving nothing. We could replace this whole inverter with a little model here of a capacitance. This would have C. This would have capacitances in parallel add. This would have twice the capacitance. This would have C equals 0. Okay. Oh, great. Filling up the, I don't know why we do this. If you're filling up a bathtub with a garden hose, it's going to fill up a lot faster than if you try to fill up an entire swimming pool. Great tidbits of wisdom for the day. If you're filling up a stock tank with a garden hose, a stock tank is like one of, you're from Arizona, you should know this. It's like a big swimming pool that cows drink out of. You're building a stock tank with a garden hose. It's going to fill up much slower than if you fill it up with a fire hose. So the amount and the water flow is like the charge flow. If I'm filling up something with a large current, it's going to fill up faster, but current consumes power. And that's why you get that current power, that power delay trade-off. If I want to fill up a very small object, I can fill it up. If I'm trying to fill up a smaller capacitance, I can fill that up faster than I can a larger capacitance. And we won't talk about the rest of the silliness. It starts to get to be like a Monty Python thing. I don't know the answer to some of these. It depends upon how much flow is going through the Colorado River and what the total thing is. Okay. So calculating delays, there's two ways of estimating it using hand calculations. If you get within an order of magnitude, you've done really good within a factor of 10. In the book, these are the equations for the average current method. You have to first calculate alpha and then plug alpha into this equation here and use that to calculate the propagation delay. There is an equivalent resistance based on velocity saturation that you should also give you in the book. The most important thing to get out of these two things, the propagation delay is proportional to C. And it is also proportional to C, to 1 over W. Turns out C, the capacitance you have with that MOSFET is going to be epsilon A over D. The area is the width times the length. So the C is a function of W. So it's going to vary. Generally, if you have a larger transistor, it's going to be faster is what usually ends up winning. If I want a faster transistor, I'm going to make W bigger. Neither one of these methods is very accurate. It puts you in the ballpark. We will get those ballpark numbers and then we'll measure them using ELDO, which is the Mentor Graphics simulator, which is what we're doing in the lab tomorrow. Now, we talked about mu earlier, and we defined mu by this equation. The velocity equals mu times the electric field. So electric field is volts per meter or volts per centimeter. Velocity is centimeters per second. If I put a higher voltage on these things, I'm going to have a higher electric field. By putting higher, and this is a pretty good approximation, saying mu is constant, until you get up to very high values of electric field here, where it starts to deviate. And I've gone through this several times, and this is like 10 to the 7th centimeters per second. It's about 0.01% of the speed of light. These electrons are zipping through this crystal pretty quickly at this point. You can't, even if you put a higher voltage on them, they can't move any faster. Because what happens is they get more energy, they just start colliding into more things, and then they lose energy, and you kind of hit the stationary point in here. There's a better approximation for mu. It's an effective thing. Mentor Graphics will take care of that for you, thank goodness. We did calculations like this back in grad school. Okay, another thing. You've seen this before. I've got, this is RP. This is like my PMOS. And RN is like my NMOS. For my inverter, I'm always going to have one of these being a small resistance, like 0.1 ohms, and one being That's kilo, mega, giga, and one's being like 1.8 tera ohms. A huge difference between these. If I put RP's 0.1 and I put 1.8 tera ohms here, pretty much all the voltage is going to be dropped across RN, and my V out is going to be very close to 1.8 volts. If I flip those, I'm going to get an answer pretty close to 0 volts. And this is kind of what's going on in the CMOS inverter. Yeah, abstract this week. Now, when we talk about power dissipation, the static power is very small, but when I build this circuit, there's actually leakage currents in here. And as the channels get smaller and smaller, as we get to smaller lengths, these leakage currents get to be larger. But pretty much for purposes of this class, we're going to say that this is 0. One of these transistors is going to be off all the time in the static situation. One's going to be on. So you always have pretty much a very small current going through there. Dynamic power is where you dissipate the most power. This is switching. This is when I'm changing states, when this inverter is going high to low and low to high. I have to charge and discharge all those capacitors. So this is what happens, and this is why the power dissipation in any CMOS device is pretty much a function of the switching speed. You increase the switching speed by 2, you increase the power dissipation by 2. There's another one, and I dealt with this when I was teaching power electronics. I used to teach 484, believe it or not. It's called short circuit current. We're going to talk about that in some more detail too. Now for the static power, if I put a logic 0 on here and it just stays there forever, doing nothing, completely boring, a 0's on here, this transistor's off. We consider that to be an infinite impedance. We know it's going to leak some current, but not a lot. This one, no, don't just stop it. This one's on. I'm having my pen just stops working at random. This one's on. This is such a high resistance, there's no path for current to flow. The current flow is really, really small. This capacitor, this is high, so this capacitor is charged up. And I don't need to charge it anymore because it's just sitting there being charged. The power dissipation is pretty close to 0. If I look at it in logic 1 state, logic 1, this transistor's on, this one goes off. I still have a high resistance path. The current equals V over R. Since R's high, I's low. This is discharged, and I don't need to charge it and discharge it anymore. The output's low. So I'm not going to draw any power. Perfect, until you start switching things. Now the issue happens here when I'm going from 0 volts. At 0 volts on the input, this is, I have a high output. Now when I switch between there, let's see, this is high, this is charged. When I switch this into low, don't hit that thingy. Okay, when I switch this into the output's high, this output goes low. I need to discharge this capacitor. And moving charge, remember, okay, the voltage on a capacitor, Q equals CV. This is the amount of charge I need to store on the capacitor to keep this amount of voltage at a given C. And I equals dQ dt. To change this amount of Q, I need to have a dQ dt, which is going to generate current. And that current's where the power dissipation is coming from. It's the charging and discharging of this capacitance on the output that gives us our dynamic power. The same thing happens here going from high to low. Instead of going from charge to discharge, I'm going from an initially discharged state to a charged state. So the current will be flowing in a different direction. But either one of those events, switching the output is going to give me some amount of current. If I switch the output faster, I'm going to get more current per unit time. I get more charge moving per unit time. I get a higher effective current, more power dissipation. So they go through the derivation of this in the textbook, but they find that doing this for once gives me a half C VDD squared. Going down gives me a half C VDD squared. When I add them two together, I get C VDD squared per cycle. And 1 over cycles is frequency. So this is a really important equation to have in your head. The total dynamic power dissipation is the frequency times the capacitance times VDD squared. So how do I get the power down? I lower the frequency. I don't want to lower the frequency. I need my data out faster. I got to zoom more. I lower the capacitance. I can do that by making smaller transistors. But here's the golden solution right here. I lower VDD, because if I can lower VDD, I get my power dissipation down by a factor of VDD squared for practically free. And this is why in the TTL days, VDD was 5 volts. And in the 80s, they decided, oh, let's drop that. We want less power dissipation. So they went to 3.3 volts. And they keep dropping the voltage power supply on these chips to have less power dissipation so that you can do more functions per chip. And now they're down to like 0.8. And they're going to keep on going as long as the transistors, you have enough threshold voltage, smaller threshold voltages on the transistors that they will still switch. This is why people do these things. Okay, the short circuit current. Let's argue it this way. If I make my VN VDD over 2, that's enough voltage to turn on this transistor. And now my VGS on this one is VDD over 2 also. So this transistor's on at the same time. I have both transistors in a low resistance state. I have basically a short circuit between VDD and ground. The peak voltage occurs at VDD over 2. If I'm between 0, if my input voltage is in between 0 and VTN, I don't have enough voltage to turn this transistor on. Then it slowly starts to come on, the resistance lowers, and it goes up to V peak. On this side, I need to keep this voltage to turn it off. It needs to be above VDD minus VTP. So this is the PMOS transistor turning on at the same time, and it peaks right in the middle. This is enough to cause a power surge in power circuits that can actually blow things apart. So power engineers, people like Dr. Yarmasu are really concerned with this. It's also getting to be a significant part of the overall power dissipation for the chip, for the CMOS devices too. Yeah, I need to explain that. Yay, okay. Dr. Brower's favorite cartoon. I would like to say a few words if you haven't heard this before. It doesn't matter how smart you think you are. We're all idiots in some areas. You got to challenge yourself and you got to practice if you want to get better at something. I'm trying to get better at programming FPGA. I've actually programmed FPGAs before. I'm just starting from scratch because it's been over 10 years. I had a high school student. He failed algebra. I got him second semester of algebra. It was the first time I ever saw him. But he failed the first semester, and the high school didn't offer first semester algebra the second semester of the year, so they just stuck him in the follow-on for the class he had already failed. He was doing miserably, and I actually started teaching that class like 4 or 5 weeks into the semester on top of that. He came to me about a couple of weeks after I started teaching, and he goes, I want to learn this. And I said, okay, come in during my office hour, or my prep period / office hour, and I'll help you out. And he really stuck to it. He was in there every day, and he was working, and every time he got stuck, I'd stop and explain something to him, even if it drove me crazy. He ended up passing Algebra 2, Algebra 1, Part 2 with a C. And was amazed with himself. And I don't, there's nobody who could not do better by working a little bit harder. It's the time you put into it, not necessarily your skill set. And I will try to prove that to you by this end of the semester by building my own microprocessor using programming. I'm going to do something hard for me this semester, so I can prove it to you that if I can do it, anybody can. Okay, we want to look at, and this is another thing we did back in EE380, these complex CMOS circuits. I want more than just inverters. I want AND gates or gates. Inverter's a nice circuit. It's easy to analyze. Let's draw a CMOS inverter. You guys can try doing this on your own. You should be able to do this. I can't check you because you're in Zoom world and you only exist as black screens for me. I actually see people in person. We were drawing this in 490 today. That's ground. There is an inverter. That's a great interview question. Micron typically gives that to people. A lot of times they will ask people to draw a 2-input AND gate as a interview question, just to see if you understand this stuff. So things that we could, logic functions we've used AND, OR, NAND, NOR, XOR, XNOR, anything else? I think those are the basics. We've had latches, flip-flops. These are mostly memory. They store memory. They store data. The rest are combinational. A counter, that would be another higher level block. Any combinational block that you want to build can be built with the following method. You've seen this before, you know, there's method to this madness. I have two PMOS transistors here. They're going ingoing, so these are PMOS, and they're in parallel. Over here, I have PMOS in series. This is NMOS transistors in parallel, and I have NMOS transistors in series. Now, if I turn either one of these on, NMOS in parallel, either one of these gates is going to be on is going to give me a short circuit path to ground. So this is kind of like a NOR function. In order to get a short circuit to ground, I need to turn both of these on. So this is kind of like a NAND function. The opposite is true up here because of the inverting nature of the gate. I have to explain this. In order to have this on, I need both of these low. So this is like a NAND. And this is like a NOR. So I flip it because I'm going to put that inversion over the whole expression. I'm going to drop the inversion from this and put the inversion over the whole expression. For PMOS, if I want an AND function, I put them in parallel. If I want an OR function, I put them in series. For NMOS, I want an OR function, I put them in parallel, and I put them in series. Most people do really good with this part in 280. If I have a more complex function, I can look at this and I can say, okay, I've got A in parallel with B. For an NMOS, a parallel connection is an OR. So this is A or B, and that A or B, the total thing is in series, the parallel combination is in series with C. So that becomes an and I've got to remember to invert at the end. If I look at the PMOS side, the A and B are in series, which is an OR. And I shouldn't have done that. A or B, and that whole thing's in parallel with C, and then I invert the whole thing. So the top function matches the bottom function, and that's the logic function. And yes, I put stuff like this on the 380 exam 1. Now a little bit harder question. If A is high, so A is high in both places, B is low in both places, and C is high, what is the output? Well, I got to figure out which transistors are on first. So a 1 on an NMOS is on, and a 0 on an NMOS is off. A 1 on a PMOS is off, and a 0 is on. Okay. Now what I'm looking for to figure out what the answer is I'm looking for a short circuit to either ground or VDD. Now if I come up this way, that's off, so that's an open. If I come up this way, I see an on, well that's off, so that's an open. So I've got an open to VDD. And coming down this way, looking through the NMOS, I've got on, so this is a short. Well, that's an open, that doesn't help me. My short circuit path, let's put this in a different color, between the output is through here. the 2 on transistors to ground. I have a short to ground, so my output is low. Okay, you get to do that on the homework and probably, maybe, possibly on the exam. Something like that. Oh yeah, I get to go back to my old exam format. You will get a standard CMOS circuit on the exam. Now, the reason why we use both the PMOS network and the NMOS network, I need something to pull up the output to 1 when I need it to be 1. The NMOS side pulls it down to ground when I need it to be low. So I need both the PMOS network and the NMOS network in order to make this work. We did something like this in the 280 lab where we had an NMOS and only inverter that looked like this. We were using this resistor as a pull-up, but that resistor always draws current. So that is a bad thing, especially when it's low. With this PMOS, we can turn off the current flow, have lower power dissipation. We can pack our circuits in tighter. So it may take up a little bit of space, but it's really helping us on the power dissipation. What do I have left? Oh, no, I know what I have left. Okay. I'm sorry. Here's another one. Go ahead and just write down for yourself what you think the logic function is. I'll give you a little bit of time. Okay, that's what I got. The A's in series with a parallel combination of B and the series combination of CD. Now, most of you who missed that probably forgot the bar. We want to figure out, same thing here. A is high. B is high. C is high. And D is low. This transistor's on. I'm just going to circle the on transistors. That's faster. Those 3 transistors are on because they have a high on the gate. And this transistor's on because there's a low on the gate. The low impedance path, somebody's chatting at me, is right here. And it is magic. The output is low. Somebody said something. Oh, good, Sean. The inversion in the expression is, if this function is true, it pulls it to ground. And that's where the inversion is coming from. Is when this function is true, the output goes low instead of the output going high. Does that make sense? Okay.
Oh, yeah. Okay, that's right.
Okay.
Yeah, I see that now.
Okay. So the next part of this, the kind of in the next part of this class, what we're going to do, this is called standard CMOS. You learned about this in EE380. Now, there are other ways you can build CMOS logic. You can build it with dynamic logic. You can build it with pass transistor logic. And it just takes up less space, basically. If I have to squeeze a circuit into a very small space, because I need to fit it like in the column of a whatchamacallit, of a memory or something like that. I have a limited amount of space to put it in. I may want to go to these other options. So we'll talk about those next. Great. Okay. Now we're getting into, oh, we want to draw this. So the first thing I want to do is figure out the logic function. So this is AD, since they're in series, and that's in series with the parallel combination of B or C, and it's inverting. Now I have to draw that same function up on the top. I think I put this on the exam last semester. So what is in series becomes parallel. So D and A were in series. I need to put the PMOS version needs to be parallel. So D, A, and then I have a parallel combination becomes a series. Oh, not this. Finger. That works. Okay, we've got an algorithm now. We put this in parallel with this series combination of B and C. So we're just flipping things between being series and parallel. Okay, I've got 15 minutes to do this. I know what's coming next. This is the new stuff. Okay. Remember, probably not. I gave you an equation a day or two ago for the RDS of the channel, and it was something like Kn prime W over L V over voltage. Okay. As W over L increases, RDS goes down, and they're inversely proportional. So this is like capacitors. When I want to find these W over L equivalents, it's like finding the equivalent capacitance using the same rules. It's kind of like an REQ for the circuit, but it's really a 1 over REQ type thing when we're finding the W over L. So all the PMOSs have a W over L of 10. All the NMOSs have a W over L of 5. And they're going to add like capacitors in series and parallel because it's proportional to 1 over that. So if I want to find the equivalent here, I'm putting these two W over L's in series. So for transistor A and B, they're in series. So this would be like the parallel equivalent. I could do, it would be 5. Did I just totally destroy your day? So A in series with B, and these are, we're going to use capacitor rules. 10 series 10 is like the inverse of 1 over 10 plus 1 over 10. We could use the reciprocal of some of the reciprocals, or we could just use product over sum, or since they're the same, I could just divide it by 2. So product over sum, 10 over 10 plus 10 is 100 over 20, which is 5. So that's those two being in series. Now that is in parallel with C, and C's 10. They're adding like capacitors, so I just add them. The W over L equivalent for the whole thing is 15. Oh, this is lab 2. Okay. Try doing it for the NMOS network. No. On your own. See if I got it right. Anybody want to argue with me? Okay, nobody's talking to me, so I'll just talk to myself. 5 in parallel with 5, they add like capacitors. So that is, I just add them, they're 10. And 10 in series with 5 is, I can do product over sum. 10 times 5 over 15 comes out to be 3.33. The W over L equivalent is going to get lower if I put them in series, and it's going to get higher if I put them in parallel. Okay. This is the new stuff. Now, oh God, that too is really fun. Now, I'm just sorry. We're only going to include the on transistors. Now, if A is switching, it's going to be on at some time, so I'm going to have to include that one. A is switching. B is low. C is high. And D is high. So I'm going to switch, I'm going to circle the on transistors. So this one, the ones that have a 1, NMOS with a 1 are on, and the NMOS that's switching will be on at some part of this. The PMOSs that are low, I'm going to circle, and that would be that one. Now we want to find, since the off transistors are going to have effectively no W over L equivalent because they have a really high resistance. Now we got to find the W over L equivalent of the top part. Okay. This is a high impedance, so I can ignore this leg because it's off. This is a high impedance through D. I can ignore that leg. I can ignore this whole leg over here because it's off. Even though it's got an on in series with an off, it's still like being off. The only transistor I need to worry about is the one that's switching, and that's A. So my total W over L equivalent for that is 10. Okay. No one's yelling at me. You must be asleep. It's the end of class. Down here, I can ignore this leg because it's off on the NMOS side. I've got effectively 3 transistors in series with a W over L of 5. I could do this, the reciprocal of the sum of the reciprocals. That is 3/5 on the bottom, which when I flip it over becomes 5/3. And I hate fractions because I can't measure them. This is
So like 1.6?
Yeah, 1.67 is what I would see when I measured it. So there you go. This is kind of like one of the homework problems, and it's one of the homework problems I get a lot of questions on. So, what do we have next? We may get out a few minutes early. Yeah, we got a summary. That's it. We'll talk about this, what we've done so far. We've looked at the transistor. We've looked at the structure of the transistor, its IV characteristics. You should be able to do problems that involve knowing the voltages. You figure out what operating region it's in and be able to calculate the current. We've looked at CMOS inverters. You should be able to, at this point, design any standard CMOS circuit using the methods that we used in 280. We haven't talked about the 4 performance criteria yet, but we will. I'll give you some hints. Power, speed, size, and one more, noise margins. I'll just call it that for now. So we've talked about performance criterion for the inverter. And I don't know what the next statement means. And now we're going to move into some more advanced characteristics of the transistor. So far, everything you've seen, we've had a number called VTN, and it was fixed. I'm going to change that a little bit. This VTN, we're going to call it VTN0. And it's actually a function of the source to body voltage. If the source to body voltage is not 0, you have to calculate the new VTN. This is called the body effect. We'll talk about that. What else we're going to do? We're going to talk about different types of CMOS logic, the pass transistor and the dynamic logic. And we're going to compare them based upon these performance criteria and see which one's better. And of course, given your application, you have to decide which one's better for that. And then we'll have an exam and we'll move on to analog. And I think I'm done. Any questions?
Those
Those 4 performance criteria.
performance
Yeah.
criteria, though, those are just like the general criteria for MOSFETs in general, don't they? So we've kind of already gone over them in a sense.
We have, but you know, the thing is that we're, you know, when we think about standard CMOS, we did that lab in 280 with the NMOS inverter and the stupid BJT inverter.
Yep.
We found that NMOS had much lower power. The CMOS had much lower power. There's different ways I can draw these logic circuits that may increase the power but decrease the size. And if I'm in a position where I have to fit it into this really small area, I may do that.
What was that last criteria on the list?
Noise margins. Yep. And so we'll look at some other ways of doing logic circuits and compare them. Usually you don't do the other things unless you're really tight for time. When you get into 490, if you take memories next year in the spring, you'll see even weirder ways of doing logic circuits. It's just like, I only have room for 1 transistor, so I'm gonna build a logic function out of, you know, what can fit in this space. You'll see all kinds of weird shortcuts that logic designers do. You know. Now, of course, you don't have the choice to do this. If you're building an FPGA, the only thing you get in an FPGA is standard CMOS. They're not trying to give you an optimization of size. It's gonna, because you've got a fixed size chip once you pick that FPGA, whether you use 10% of it or 100% of it. They're gonna use stuff that's reliable because they can't control the way you're designing it. And you'll definitely be using standard CMOS in there, whether you realize it or not. And if you want to shrink things down because you're like, you know, you're at Micron and you want to sell these custom chips, you can get a much smaller die and a much lower cost by using custom circuit design, which is what I did. I did full custom on a level most people have never done in their life. And part of the reason for that was we started out, some of the physicists had the idea of we're going to bury the photodiodes in the substrate. And when we did that, every manufacturer said, you're violating our design rules. And we got like 1 or 2 of them that would say, okay, we'll build this for you, but there's no guarantee that it'll work. And so I said, okay, we'll do it. And then everybody who sold things like standard cells, IP for things that were already done, microprocessors that were already built, just looked at us and said, no way. We're not selling you anything. So we had to start out, first of all, designing our own transistors, designing our own AND gates, designing our own flip-flops, all the way up to designing our own ADCs and microprocessors. And there'd be like 5 people doing this whole thing. And I was one of them. So, and there's not many people who do this. So I've seen quite a bit of the design cycle. I've even done.
How much did it end up costing?
No one estimates our time. We were just a bunch of people at Caltech. So we were on salary. Generally, to produce them would be about $100,000 to get one ran, but it would generally, from bottom to top, it would take 5 engineers about 6 months of our time. So that you factor in our salary, and on top of it, there was our tool cost, because Mentor Graphics at the time was charging us. It was a brand new thing, and it was really cool. We liked it. But they were charging us $250 an hour to use their tools. So our IT bills were in the hundreds of thousands of dollars a year too.
Criminy.
Yeah. But who was paying for it? These people from the government who had wheelbarrows full of money. Thank goodness they exist. We designed the world's first wireless camera. Nobody had anything like this before. We designed a camera that you could put on a backpack on a cockroach that was radiation hardened, so they could run this thing up into places where people were like building dirty bombs and things like that and spy on them. And we were the only ones building things that were anything close to that, so they were willing to pay the price. We had a wireless camera you could fit into the, it was like James Bond stuff at the time. You could fit into a size of a cigarette pack. That was the goal, and take pictures. And this was before everyone had cell phones that took pictures like that. Okay, this is how your government spends your money, entertaining engineers.
You ever think they'll be more lenient on IPs? That way it's like easier to get a hold of that stuff rather than having to like design it on their own or something like that?
Nowadays, the CMOS image, the technology we invented is the camera that I'm using to talk to you with. It's the $5 camera that's everywhere now, and it's probably cheaper than that. So yeah, it's there, and now it's standard mainstream stuff, and so people have, manufacturers have developed processes that are good for these, burying these photodiodes in the substrate, and so now it's become standard, and you can buy the IP for it. But anytime you want to do something new, that's when you get to do something fun. Like what I'm going to do next is build a crypto processor. Because I have to do it from scratch, and that's what I do. Yeah, it's hard finding work like that.
Thank you, Julie.
Okay, I'll see you guys on Tuesday. Or I'll see you tomorrow in lab.
Yep. See you, lab.
Okay, bye.
I have a few questions.
Okay, sure.
The R. Can I
Yeah.
share my screen?
Yes, okay, wait, hold, yeah, you should, wait, let me do the stop share. Now you can share the screen.
All right.
Thank you, Miss Julie.
Okay, we'll see you.
So here, is this equal to this one, this part?
Gamma, no. Oh, okay. Let me see what, let me pull this up. This is slightly weird. I think you have to think a little bit to do. That's lab 2 pre-lab. Why is that the lab 2 pre-lab? It looks like the lab 1 pre-lab. Okay, lab 1, inverter 1. What is the pre-lab? Oh, this is the easy one. Okay, so that is for lab 2, is what I gave you.
So this is for pre-lab, the VM.
This is, oh, the VM, you're right.
Yeah.
Okay.
So I need to use R.
The R, where does that come from? The
So-
R, okay, so R equals mu W.
Is it
Oh,
KP or KN?
KP over KN.
Which
Now,
is
there's another equation, which is an equation sitting right next to it, right? Mu W. KP, KP prime also equals mu Cox.
wait, the K. This
KP,
one
yeah, KP prime, this one right there, right? Yeah,
on the left.
that equals mu Cox. I don't know if I can draw on the screen right now or not.
1 second. I
No.
think I need to share remote control.
Okay. So,
I think, can you now?
no, let me try my finger. No, I can't.
Mhm.
Okay. So another expression
Yeah,
for
I get. Yeah,
the-
now controller. My
yeah,
screen.
oh, okay. K, no, it's not letting me draw.
Oh,
Okay. And just write this down. KP prime or KP equals mu Cox. Mu P Cox. Kn prime equals mu N Cox. So the Cox is going to cancel out, and you can use the ratio of the KPs is going to be the same thing as the ratios of the mu's. And you can get mu somewhere. Oh, no, even better than that. Page 1 of lab 1, it gives you numbers for KP and KN. Go back. Go, yeah, right there. See, it's giving you numbers for KN and KP.
so I use this number.
Use
for
those
this-
numbers. Yes.
So KP, this one is equal to the normal KP.
Yes.
Oh, okay. Okay, makes sense.
Okay. And then once you do that, you can get multiply that by W, and you get you get R. Oh no. Okay. Oh wait, a little bit more complicated.
I use this equation to get R.
Okay. So this is KP and not KP prime.
Yeah, this is KP, not prime. Is it
Right.
equal to prime?
But
KP
the ratio of the mu's is going to be the same thing as the ratios of the KP primes. So you could replace mu P
with KP prime.
with KP prime.
Okay.
And you should come up with a number that's about 2.76.
Okay. I think that's it.
Okay.
Thank you.
All right. Okay. I'll see you.
See you tomorrow.
Okay. Bye.
Bye.